we've been talking, excuse me, we've been talking a lot about these cubic and fifth degree, seventh degree polynomials. These polynomials have odd degrees, and that's intentional. My hope was to kind of shed light on these because we haven't dealt with them a whole lot in our experiences through Algebra 1, Algebra 2, and so forth in this course. Okay. So my hope is that we understand those end behaviors. We've dealt with these quite a bit in the last couple of days. My suggestion to you is not to memorize all four of these graphs. My suggestion to you is to learn this one. Okay? And then the one directly to the right of it is simply the result of multiplying a function by a negative, which is one of our transformations that we should already know from the last chapter, and what that does to y values. Okay? So these two are kind of linked with that relationship. So instead of learning two things, learn one thing. Okay? And something that you already know about transformation. The next two pictures, my hope is that we don't even really have to talk about these very much because they are even degree polynomials. And what is the number one even degree polynomial that you've had experience with? 2. Yes. Okay. So x squared, any quadratic, you understand that if this was a quadratic, it would look like, it would look kind of like that, right? Okay. Where the dotted part here on the one that was on the picture is showing that we can have different behaviors here if it's to the fourth, to the sixth, to the eighth, all that kind of thing. But regardless, if it's even, the end behavior, which is that portion and that portion, or this portion and this portion, is exactly the same as it would be for x squared if it was concave up for that first picture or concave down for the picture on the right. Does that make sense?
Yeah.
Okay. Ladies, let's sit in our seats, please. So then, when we go through and talk about the end behavior of these two functions, my hope is, again, we only learn that one, and I'm going to say, do I learn that, or do I already know it because I know x squared very well? My hope is that we already know that, right? And if I multiply by a -1, which is a x-axis reflection, I get that end behavior. Okay? So those are some thoughts that hopefully kind of condense those four pictures and all the information that's existing in those pictures into really just kind of two ideas. Okay? Is that okay? The discussion I think that needs to take place in regards to end behavior, and I kind of talked about it yesterday when I started highlighting and whiting stuff out up here. That term right there is really the only term that dictates end behavior, the leading term of any polynomial. Okay? So I want to go through the algebra with you that confirms that verifies that that's true. Okay? So let's start with a function. Give me a number.
7.
X to the, let's go fifth. Yeah, when you say things, I just get a negative response. So, so negative 7x to the fifth plus, let's go, 6x to the third minus, 5, I don't know, it doesn't matter what the coefficients are, 5x plus 10, 21. Doesn't really matter what power we start with, what exponent. Doesn't matter the coefficients. Doesn't matter the constant term. Doesn't matter that I'm skipping an x to the fourth or an x squared. I want to show why, no matter how many terms you have up there, like we've got, 5 up there now, if I had 25 up there, the one with the largest degree is going to dictate the end behavior. Okay, I want to talk about why. The first thing we can do is say, well, what if I plug in just some numbers here? Okay, just some large numbers of x. Okay, well, let's say that x is 100. If I take 100 and raise it to the fifth power, how many zeros does that give me? 2 zeros raised to the fifth power should give me 10 zeros, right? Okay. So I'm going to have negative 7 times a 1 with 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Plus then, when I put 100 in there, I'm going to get 6 zeros, right? It's going to be 6, 1, 2, 3, 1, 2, 3. And I plug in 100 here, it's going to be 500. And then plus the 21, right? If you are in debt that much, so there's a million, right? There's a billion. So you're in debt negative $70 billion. And you go buy something that's worth $6 million. Is it really? Or you pay off $6 million of that. Did you really do anything? No, you're still in debt, right? That's like taking $100 and subtracting 6 cents from it. It really doesn't do anything. Okay? So this 6 million here is what we refer to as a negligible amount. Okay? It doesn't really impact the y value. I'm at negative 70 billion. Add 6 million to it. I've just moved up a fraction of a movement, not even putting a dent in it. Okay? Well, if that doesn't put a dent in it, then 500 ain't going to put a dent in it, right? And adding 21 to it ain't going to put a dent in it. So does it prove to you, at least that way, that which is coming from that, is going to dominate our functions and behavior when x gets big? Now, here's my question. Is x really big with 100? No. Okay? It happens really fast, actually. Okay? Because x is relatively small when it's 100 compared to what it needs to be in the long run of infinity. Okay? So the idea is, okay, well, what if I plugged in x to be a billion? What does this become? Okay? So a billion would be 9 zeros, right? So then the fifth would be, ended up giving me 45 zeros. Okay? So a negative 7 followed by 45 zeros is going to be a very, very large number. This would even be big. So put a billion in there, so 9 raised to 30 would be 18 zeros. That's still a large number, right? But it's it's a dwarf size number and compared to a negative 7 followed by 45 zeros. So these are negligible amounts. Excuse me. I don't know if I'm getting sick or what's going on. I don't feel sick, but I hurt. Okay. All right. Let's do this algebraically. And we could maybe better do this if I took out or maybe prove this more along the lines of a general case. If we took out the 7, the 6, the 5, and the 21 and replaced them with like A, B, C's, D's, and E's. And the same thing with the 5 and the 3 as exponents and the 1. We use n minus 1, n minus 2, that kind of stuff. We could do this algebra and come to the same conclusion. But I think it might be a little more obvious of what to do if we use these specific values. So what I'm going to do is I'm going to rewrite f of x. I'm going to rewrite it conveniently. I'm going to divide everything by negative 7x to the fifth. If I divide everything by negative 7x to the fifth, is that the same thing as factoring a GCF of negative 7x to the fifth out? Okay, so when I do that, it's going to be negative 7x to the fifth over negative 7x to the fifth plus 6x cubed over negative 7x to the fifth minus 5x over negative 7x to the fifth plus then 21 over negative 7x to the fifth. Okay, if I were to distribute this GCF right here back through all this stuff, I would just essentially cancel all these denominators out and leave me with just the numerators, which would be exactly the same thing as this, right? So I haven't changed the way it looks, I haven't changed what it does. Okay, so let's go through and simplify the things that are in the parentheses. Negative 7x to the fifth divided by negative 7x to the fifth is 1. Plus then, okay, so this is going to give me what? Negative 6 over, 7x squared 3 and 5 cancel out, give me 2 on the bottom. This one's going to be plus 5/7 x to the 4th on the bottom. Is that okay with everybody? That one cancels that. And the last one is 21 over negative 7x to the 5th. So you can change this. I got positives and negatives back to back. You can change this if you want to, but don't really care. Here's the idea. In behavior, that's what we're trying to focus on here. In behavior tells me what is happening when x gets what? When my x values are what kind of numbers? Big numbers. Okay? And now I'm going to think very, 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 very big numbers. Okay? Like I'm thinking infinity minus 1. Okay, fine. Okay? If I do that, if I take a very, very, very big number, okay? Let's say that you know what a Google is? No. So it's a 1 with 100 zeros behind it. Okay? If I plug that in here, I then get a 1 with 200 zeros behind it, right? Take a 6. Take the number 6 and divide it by 7 followed by 200 zeros. What would that number be very close to? It'd be close to 0. Okay? It's not going to be 0, but it'll be very close to 0. But here's the thing. Okay? If I have a number like 7 followed by 200 zeros, you guys would think that's, I'm thinking like dollar amount, that's a pretty ridiculous amount of money, right? Yes. But if I'm thinking about it compared to infinity, is that actually a small number? Chump change. Yeah. Okay? So even though to us, 7 followed by 200 zeros is huge, in comparison, in relativity sense, it's small compared to infinity. Okay? So you can imagine then, well, what happens if I get to infinity? Even if it's a 7 followed by 200 zeros goes to 0, then infinity is going to make it go to 0 even much faster. Does that make sense? Yeah. So that amount right there, negligible at 0. Okay? When x is really, really big, this is 0. Well, think about this then. Okay? Isn't that, because that's x to the 4th now, isn't that going to go to 0 much faster? When I plug in a Google right here, that denominator becomes so much bigger than the denominator that was right here. Well, 5 divided by a much bigger number than was right here is still going to be 0. And over here, same idea, still going to be 0. Does that make sense to everybody? So, and this is the idea of what we call a limit. Okay? I'm right now trying to evaluate as x goes to infinity my f of x function. Okay? You don't need to write that down. But I'm trying to plug in infinity for that x value, that x value, and that x value and see what happens. Well, it gives me negative 7x to the 5th, and now I have 1 plus 0 plus 0 plus 0. What's 1 plus 0 plus 0 plus 0? 1. So I got negative 7x to the 5th times 1, which is just negative 7x to the 5th, right? What is that function? Isn't that the same thing as the leading term that was up here? Okay. So now I'm gonna redo this limit again. I'm gonna say, okay, limit of f of x now as x goes to infinity, and now I'm only interested in using negative 7x to the 5th. Okay. If I plug in a very, very, very large number that's positive, and I raise it to the 5th power, what kind of number do you get back? Positive. Okay. And then you multiply it by a negative 7. Okay, so plugging a very large x value right here to x to the 5th gave me a positive back, right? Multiply by a negative 7, what's it give you back? A negative, right? So what we're saying is as we get out here to x being infinity, your y value is going to go down to negative infinity. When I plug a very large negative number in, and I raise it to the 5th power, what kind of number do you get back? A negative times itself 5 times is negative, right? Multiply it by a negative 7, what kind of number does it turn into? Positive. Is that the exact picture right here? When A is negative, so negative 7 here, and you have an odd degree, is this the end behavior that we get right there? Is that what we demonstrated right here? So the idea is, no matter how big your polynomial is, we don't care about the 6x to the 3rd minus 5x plus 21. Because that's chump change in regards to my y value, when I first evaluate with the negative 7x to the fifth. Okay? Now, that change, as we get closer and closer to 0, obviously that changes. And those other terms become more important. Okay? When x is huge, those extra terms are meaningless. Okay? So that's all we need to be able to do is pay attention to is that leading term. So to determine the end behavior of this polynomial, okay, my hopes are, guys, we don't do any evaluation. We don't do anything but look at the leading term. What's the leading term here? Negative 2x to the fourth. Okay. One thing I would be cautious on. The homework assignments will do this. The tests and quizzes that I give you will absolutely do this. Your leading term is the largest exponent, right? Or the term with the largest exponent. Does that mean it always has to be the first one? No. They might scramble them, okay? And I do this because I want to make sure that we understand that concept. I want to test two things. One, do you know what the leading term is? And two, do you know what it does? Okay? The leading term, by definition, is the one with the largest exponent, the highest degree. Okay? It's not always the first one. Okay? By definition, it's the one with the highest degree, highest exponent. So we might scramble these. Just make sure you pick out the one that's the largest. Okay? In regards to the degree or the power. So now, my hope is you remember, well, if it's even, it's just like a parabola, right? Yeah. Its end behavior is just like a parabola. A parabola, x squared, is like that, right? But then I remember, but there's a negative out in front. So what's a negative in regards to transformations do? Flips over the x-axis. So the red would actually be what is happening here in the end behavior, right? So I would write down then as x moves that way. As x goes to positive infinity, y goes to what? As x goes this direction, where's your y going? Is it going up or is it going down? Going down to negative infinity. Yeah. As x goes to negative infinity, as x is going this way, where's y going? Careful. Following the red, right? So it's going to go negative infinity as well. Now you might be asking, well, why are we doing this? Here in a little bit, guys, we're going to put together some rules, some procedures for graphing any polynomial function. This is one of the first things that we have to do to graph any polynomial function. Find out what it does at the end or the outsides of its graph, and then we go start working our way towards the middle, towards 0, 0, and see the other behaviors. Okay? Is that something we can do? Is that pretty easy? Okay. Here's the actual graph. Okay. So like I said, eventually, what we just did was finding that there and that there. Eventually, in the next couple of days, the hope is to be able to decipher then working kind of towards 0, 0, what we're doing there in that dotted region. Cool? All right. Yeah, I assigned something today. All right, you don't need to write all this down. I would write the box down, but not everything up top. It's not important. Or it's important, but it's not important right now. So if P is a polynomial function, C is called a 0 of P, if P of C equals 0. Okay. So C is some random x value. Okay. If I have some polynomial, and I plug this x value in that they're calling C, and I evaluate my polynomial at that number, and it evaluates to give me 0 back. It gives me essentially a y value of 0. That means I would plot point C, comma 0, right? Well, C, comma 0, plot that, or, let's say C ends up being the number 3. If I plot 3, comma 0, what kind of point is that? It's an ordered pair, yeah. But with a y value of 0, it's a x-intercept, right? Okay? And that's all this is saying here, okay? Because when you evaluate your polynomial at some number, and it produces an output of 0, and that number you evaluated at was what we call a 0, because it produced a y value of 0, okay? Then we get the idea then that x, if we say x is equal to c, we call that x equal to c an x-intercept. Now, you're going to hear different words being used, and I'll try to explain the differences between them as we use them. But if I look, and then this is just the way going off of what you talked about in Algebra 1, the Algebra 1 textbook. If we have the words root, 0, or x-intercept, okay, we all kind of talk about those in the same way. We almost say that they're synonyms to one another. And I will interchange them and use them as the same thing over and over again. The idea here is if that's my C value, okay, then the C is what we call the 0. C comma 0, that ordered pair off of Algebra 1 says that's the x-intercept. Does that make sense? Okay. In previous, so it's never an issue, kind of like a paper and pencil test. But if you give you something on WebAssign or previously when you guys used Math Excel, if it said write the x-intercept and somebody just wrote whatever the C value was, they were at like 3, it counted wrong. They want 3 comma 0. Does that make sense? Just a notation thing. So it's a verbiage thing, not a big deal. But some people ask, well, why are there 3 words for the same idea? It's just because one refers to just the C value, one refers to the ordered pair. And we'll talk about roots later on, what that refers to. But if C is a 0, so think about this. If I go, let's say our P of X kind of factored down to like X plus 3 and X minus 4, you eventually got down to X equals -3 and X is equal to 4, right? That's kind of that line right there where they're saying X equals C is a solution of the equation P of X equals 0. So this here is a solution to the equation when that is 0. Okay, so that says the same thing, that C is a 0. They're saying that if I work backwards, okay, if I said X equals -3 was a solution or a 0, then X plus 3 must have been a factor. Does that make sense? X minus 4 must have been a factor. Okay, so that's this line here. And then the idea is, well, if those were zeros or solutions to the equation, 0 equals X plus 3 times X minus 4, then that C value of -3 and the C value of 4 are also x-intercepts as ordered pairs. So when I give you an x-intercept, you automatically know a factor of your polynomial. That's what we're trying to get at here. If I tell you your x-intercept is 5, you know automatically that x minus 5 was a factor of your polynomial. Is that okay? Okay. If I tell you that you evaluated your polynomial at 4 and you got a 0 back, you automatically know now that x minus 4 is a factor of your polynomial. Okay. So those are some terminology things that we need to kind of justify and come to terms with. All right. I'm going to skip a little bit down. We don't need to write that down. We should probably talk about this concept. It's called the intermediate value theorem for polynomials. So it says for polynomials. So what will I always be working with here?
Polynomials.
Polynomials. So when I read this statement, I need to know in the back of my mind, what are the properties of polynomials? Okay, because I know I'm dealing with polynomials, right? Yesterday, we said if we trace a polynomial with our finger, it is always going to be, if I can trace the whole thing with my finger, what was the word that we used for that? Continuous. Okay? So when I interpret this theorem here, I need to realize that continuity is something that is integral to this theorem because it's for polynomials. It says, now I'm going to read this. In my opinion, you've done this in an English class, you've read a book, and you just read it, and you just keep reading, and maybe a half hour after you finish reading or whatever, you say, well, what the heck did I just read? I've done this so many times with books that aren't interesting to me. I read them, and once I'm done reading it, I say, okay, what I just read a bunch of words, I didn't really take any of that in. I didn't comprehend any of it, right? You've done that, right? All the time. Okay, I think that happens every single time that I read a math theorem, okay?
I have to sit down and break it down into pieces, draw pictures, that kind of stuff to justify it, to make sense to me. Because if I say if P is a polynomial function and P of A and P of B have opposite signs, then there exists at least one value C between A and B for which P of C equals 0. When I'm done reading, I think, what in the world did I just say? What did I just read? Okay? So let's break this apart. Let's see what this should be. Ultimately, a very kind of elementary or common sense, obvious theorem. Okay? But drawing the picture is going to help us get that one. All right, so we know we're talking about polynomials, right? You said polynomials are continuous, right? Okay. So it says if P is a polynomial, and P of A, what's P of A? When I say something like that, what is that referring to? What is that notation? P of A, P of 3, P of 12. P is my polynomial, so P. Okay, so A is the x value, and then P of A is the what? It's the y value. Okay, so then P of B is an x value, and P of B is a y value, right? Okay, it would be much easier to understand this if they were to say that, right? They don't want to spend a lot of time writing that out, so they use the notation that we hopefully learned. So P of A is a y value. So I'm going to say A is right here. And let's say that B is over here. Okay, you can put A and B anywhere you want, you guys. It doesn't matter. Okay? And it says P of A and P of B. They have opposite signs. So that means one y value is positive, one y value is negative, right? Doesn't matter which one's which. I'm just going to say P of A has a positive y value. And we'll say P of B has a negative y value. So there's P of A. Right? All right, I guess this is the point A, comma, P of A. This would be the ordered pair B, comma, P of B, right? Is this okay with everybody? Have we satisfied everything that's said in this hypothesis? Okay, if that is happening in front of us, then there exists at least one value C between A and B. So one value C somewhere in that blue region, for which P of C equals 0. What's P of C equals 0 mean? The y value is, you're saying that your C value that you plug in, that is between A and B, is going to produce a y value of 0. When I have a y value of 0, it produces a x-intercept, right? So they're saying maybe that's C. Here's the idea, guys. And this is where we have to understand that polynomials are continuous. If I have my finger on A, comma, P of A up there in the first quadrant, and I know that the polynomial goes through B, comma, P of B, and I got to get from point, call this point A up here, to point B down here. Okay? And it's continuous, so I'm not allowed to lift my finger, right? Don't I somehow have to cross the x-axis? What's the word intermediate mean? Just by itself. In the middle. And that doesn't have to be in the exact middle, but between, right? Intermediate kind of means between. So this is saying that if you have y values that change signs, then what did you have to cross between those two y values? You had to cross a value of 0, right? Okay. That's all the intermediate value theorem is saying. But what's nice about that, guys, is let's say, okay, I've got a polynomial, and I don't know what its expression is. Let's just say, I'm going to write an expression here. Don't know what it is, don't care what it is. But I evaluate P at, let's say, 3. And I get -5 back. And then I evaluate P at 6. And I get +6 back. And I'm looking for 0. Maybe I don't know how to factor this, but I'm looking for zeros. The intermediate value theorem now just says at 3 you've got a negative back, at 6 you've got a positive back. So somewhere between 3 and 6 there should be a crossing. You should cross the x-axis. So there should be a 0 between 3 and 6. So when I'm trying to narrow down what my x-intercepts are, I'm not going to try something like 7 or 8 or 9. Okay? I might have some zeros out there, but I am guaranteed if this is 3 and this is 6, and this gave me, let's do it this way, let's make that positive 5 and this negative 6. If that gave me positive 5 back there and negative 6 back there, I'm guaranteed between that 3 and that 6 that there's going to be a 0 somewhere. That's what the intermediate value theorem gets at. Do you guys think that's kind of obvious? That's kind of simplistic, right? But when I read that statement initially without the picture, I don't think that's not that obvious. I think there's a lot of terminology, a lot of notation in there that kind of throws us off. All right. And the reason I talk about that stuff, guys, you're going to be at some point in a science class, a math class, maybe an analysis class or something like that in college. And you're going to have theorems. You're going to have these rules and these properties, and you're going to have to read them and understand them. Okay? And you have to kind of pull them apart, pick them apart. I want you to have that skill to do that. Okay, so here are some procedural steps that these are guidelines. Okay, so they're not set in stone. Guidelines are just suggestions to grasp every polynomial function we talk about. Okay, what's going to happen, guys, as we start talking about third degree, fourth degree, fifth degree, sixth degree polynomials, the larger degree polynomials, our graphs are going to be a little bit fuzzy on the kind of the interior of the graph, okay, on the relatively close to 0, 0, okay, and we'll kind of talk about that as we start seeing examples. The first thing we're going to do is we'll find zeros, okay. The fact of the polynomial, we find all its real zeros. Those are going to be your x-intercepts. Okay. When they say factor, I mean what that means. That means all your factoring skills that you possess. Okay. Perhaps some technique, AC method, quadratic formula, use substitution and the quadratic formula together. We got all kinds of different factors. GCFs. Later on in this chapter, we'll get to P over Q, and that will be the default that allows us to factor pretty much any polynomial that comes across. Okay? Is that cool? So they say factor. They're talking right there. It's about 2 years of math that you've already learned. Okay? Step 2 is where things get kind of fuzzy. Okay, if I have to use test points, this isn't really then all that of a efficient or even a precise task. Okay, because I'm not sure maybe what test points to choose and that sort of thing. Okay, now the intermediate value theorem might suggest some ideas and present us some concepts to use. But it says make a table of values for the polynomial. Take some x values that are logical x values, evaluate, see what the y values are that come back. Okay, and it makes sense to do that after you've already chosen some zeros. It says to make sure that your y-intercept is also one that you include. Y-intercept, when I do my zeros, I always find my y-intercept right away as well. Okay, that's pretty easy to pull off the function. Okay, in behavior, we've already talked about that. Okay, that needs to be a component to our graph. Once we have all that data, all that information, we throw it all together on a graph, and hopefully we then get a comprehensive picture. Okay. But again, because we had to use test points, and we don't know the calculus yet, to allow us to find the best points to use, this is still going to be kind of fuzzy. Okay. When you get to calculus, you'll use derivatives. You'll find things called critical points. You'll find inflection points. And it's actually, I think it's kind of a fun thing to do. When you get to that, when you start learning that calculus, it's not hard. All right, so let's skip over. We'll come back and do these examples. I want to skip down to talk about this idea before we get there. I want to kind of just discuss all the things that can happen in a graph, and then when we go back to do an example, we have everything that we kind of in the back of our mind. We got all the different relationships that could happen, all the different images that could show up, and it should be easier collectively to do it once we know all this stuff. All right, so the shape of the graph near a zero. Shape of a graph near a zero. You guys remember if we were to say, let's say P of x is equal to x squared plus 8x plus 16. What's that factor to? Okay, so x plus 4, x plus 4, right? So now if I use the 0 product property, that's going to tell me x is equal to negative 4, and x is equal to negative 4, right? When I graph that, how many intercepts do I really graph? Just one, okay? So, this is a parabola, right? If I'm only graphing that one at negative 4, it's concave up or down? Concave up, so that has to be the vertex. Good. That has to be, why does that got to be the vertex? Think about it this way. Doesn't this mean x plus 4 quantity squared? That's what x plus 4 times x plus 4 means, right? If I add 0 on that, is that in a times x plus h squared plus k form? And then we see that negative 4 comma 0 would be the vertex. Here's the thought. When you get two solutions like that are the same, graphically, parabolas have that symmetry. If my parabola passes down through the x-axis one time, it continues down through the x-axis, then it's got to pop back up and pass through the x-axis a second time, right? And the algebra should verify that. Here, the algebra says you only get to go through the x-axis one time. So if I only go through one time, this cannot happen. Does that make sense? Because parabolically, it needs to come back up, and it would have another 0. Well, this algebra says you don't have another 0. Okay? Does anybody remember what it does here? You said it was a vertex. What's the word we use here for this graph when it does just something like that? T. What did it mean when I had that circle and that line touching? Okay. So we're saying the x-axis here is tangent to the parabola, okay, at the parabola's vertex. Now, you guys remember what you guys talked about that as being in algebra? Called this a double B. Ever heard double root? Nope. Never heard that? Okay. Maybe multiplicity of 2. Okay, so multiplicity means that's how many times it showed up, right? How many times it's a factor, how many times it's a 0. Okay? What we need to know, and this all comes from the idea of taking a negative number and squaring it. Negative number squared gives you what? Positive. Positive number squared gives you positive. So numbers to the left of negative 4. Numbers to the left of negative 4, like negative 5, will give me a negative here and a negative there, right? If I take a negative and square it, it's going to be a y value that's positive, right? To the right of 4, or negative 4, so like negative 3, that's going to be a positive and that's going to be a positive, right? So positive times positive is positive. So the idea of multiplicity is talking about how many times are you multiplying a negative number? Well, here I'm multiplying a negative number twice, so it's going to turn into a positive number, right? Okay, so what if this was what if I had f of x equals x to the 4th? Let's not go x to the 4th. So x minus 4 to the 4th. And how many times am I multiplying a negative number? So if I go to negative 4 here, I plug in like negative 5. Okay? How many times am I going to multiply a negative number? 4 times. And a negative multiplied by itself 4 times is a positive. So when I've got x values that are over here, my y values are going to be up there, right? They're going to be above the x-axis. When I plug in a number to the right of negative 4, so like negative 3. Negative 3 minus 4, negative 7, right? I guess I should get plus 4. We're going to go negative 4 here, but it doesn't really matter. But if I go negative 3 plus 4 is 1, right? 1, positive number multiplied by itself 4 times should be positive, right? So I cut there again only one time. I'm tangent to that point. Okay? So here's the idea. When we have function, start at 2 here. All right, so that's your problem, right? X plus 4 squared. Multiplicity of 2. Here's x plus 4 to the 4. That's multiplicity of 4. It's the same behavior there at negative 4, though. Are we tangent to negative 4? Yeah. Okay. If I go multiplicity of 6, do I end up being tangent at negative 4 again? Yeah. Now you might be thinking, well, it looks like it's more like horizontal here and kind of bottom out there. But as I zoom in, no matter how far I want to get close to negative 4, so let's just say, that's pretty close right there. I should be able to zoom in far enough to where you see the curve and the x-axis. You see they separated there, right? Okay. The only place they won't separate is negative 4. Okay. So to prove that, I would just zoom in on this. But as you zoom in, so it's never going to, because we're getting so close, you're not going to see it ever separate. And I could just be doing this all day long. So it's going to be.
I want to see it separate around it, though.
I don't know that it will show that, because we keep iteratively getting closer and closer. So it just, see there, it just disappeared.
What did you say?
Iteratively.
Did you call me an idiot?
No.
No.
Just same thing over and over and over again. Kind of just chunking it down. Does that make sense? Zooming in, doing the same process. Iterative, doing the same thing over and over and over. So here's my question then. What happens when it's odd? Because that was an even multiplicity, right? Let's make it an odd multiplicity and see what happens. So linearly, we know that every line should pass through there, right? Okay. Now you guys know that if I had x plus 4, and in algebra 1, the plus 4 was our y-intercept, right? We can also view that as a negative 4 as being your x-intercept. You can graph them that way if you want to. But let's go cubic. When I take a number to the left of negative 4 and I put it into x plus 4, it's going to be a negative in that x plus 4, right? What's a negative times a negative times a negative? A negative, and that's why my y value is negative down here, to the left of negative 4. But if I plug in a number to the right of negative 4, let's say I plug in negative 3. Negative 3 plus 4 is positive. What's a positive times a positive times a positive? Positive. So the idea of multiplicity, tell me, if you're multiplying a number that is negative an odd number of times, the result should be negative. If I want to take a positive number and multiply it by itself an odd number of times, the result should be positive. So what does that mean? It means essentially what the intermediate value theorem provides us. If that value right there has a y value that's negative, this one has a y value that's positive, and somewhere in between there's got to be a 0. You have to pass through the x-axis to have that happen. Okay? N to the 5th, n equaling 5, do the x plus 4 to the 5th, same behavior. Same behavior when it's the 7th, and so forth. Does that make sense? Yeah. All right, so what we'll do, and we'll start with this tomorrow, is that they'll give you Monday, yeah, whatever. We'll give you that P of X up there and ask you to graph it. Okay? First thing we have to realize, though, is what degree is that? Okay? So we have really that's x to the fourth. That x minus 2 cubed will actually boil out to be an x cubed. And x plus 1 squared will actually multiply out to the x squared, right? So x to the fourth times x cubed times x squared, it's actually going to be an x to the ninth, right? So if it's to the ninth power, I automatically know my end behavior. As I move to the right, y's are going up. As I move to the left, y's are going down. I know my end behavior right away. I know my zeros of 0, it's a multiplicity of 4, though. I've got a 0 of 2, it's a multiplicity of 3, and it's a 0 of negative 1, but it's a multiplicity of 2. And I should then be able to graph that pretty comprehensively and pretty quickly. Okay. The hardest part about that question is to figure out what the leading term is, what power it is, and then to factor it if it's not factored for me already. Have a great week, and there is a homework assignment. Let's not do Monday. Not do Monday. See you, Chuck. Morning, Elijah.